A huge warm welcome to everybody joining us on our webinar today. This is our last webinar of 2023, and we know that we've got lots of new people joining us for the first time today. So we're very excited to have you here with us, but also all of our regular webinar guests that join in every other week to hear us talk about all things Wi-Fi. And today, the webinar topic is going to be around how does RF noise affect the speed of our Wi-Fi performance, and it's featuring our superstar device, which is our Ekahau Sidekick 2. So in the agenda today, we've pretty packed. Mac, how's it going to be going today?
Okie doke. So we will kick off with the latest and greatest in the AI Pro because we've updated it recently, and honestly, it's super cool and super helpful. The new features are amazing. So we'll take a look at that first. Then we'll talk about noise. So we'll talk about Matt because he produces a lot of noise every time we are together in meetings and working together and stuff like that. So we'll talk about what the noise is, what causes it, and how can noise and interference affect your Wi-Fi speeds, data rates, how to measure it, how to optimize it. And instead of just talking about it, we'll actually show you a few demos about and around noise.
Amazing. Well, in that case, then we can hand over to Mike, who's going to be doing a few demos to bring you up to speed with what's come out with Ekahau AI Pro this year, what you can get your hands on right now. I think Mike might have a slight sneak preview up his sleeve for something coming up very, very soon in the next new year.
All right. Hey, let me share my screen. Hope you guys can see what's happening on my screen right now. All right. So let's start with some kind of recap, what we brought during this year. And as you can see, that's the white theme. Like there were so many requests for the white theme, and here it is. It's pretty cool that you can like choose like which side you would like to join, like the dark side or the light one. Now you can prove on which side you are. This is the white theme, right? But at the same time, we got something else regarding the interface. You will be able to, you're ready. You can do it like you was able to do that like a couple of months ago, but nevertheless, you can scale the whole interface. For example, if those icons are too small or you would like to fit more stuff in your list, you can go to your settings. Actually, same applies to your Windows machines and do it like this. Pretty cool, right? So now everything's smaller. If you want to go with the bigger fonts or bigger icons, no problem. But for Windows users, let me show you how you should go with. You should be able to change the interface scale from the preferences here. Don't forget to restart your AI Pro, by the way. So this is the one thing, but let's move to the features that are more about the AI Pro stuff. The sharing, damn important and damn easy nowadays. Just like save your file somewhere to the cloud, press the save to cloud, and once again you will see the pop-up that where you just need to type your friend's email or someone who you would like to annoy with some notifications that something was just shared with that person. So yeah, and if we're talking about the integration, it's not only about sharing, it's also about the optimizing, right? Because if you would like to optimize your project, just go to the inspect workspace and press this fancy image, and that will open the optimizer. It will tell you what you can do and what you cannot or what should not do with your network, and it will help you to make better Wi-Fi. All right, since we're talking about Wi-Fi, let's switch to the APs. What we can do with the APs. Here's my fancy pink AP, by the way, with the star. It's like a rock star stuff, but everyone should be able to do that, right? Just go to the view and select the measure distance. In this case, you'll be able to measure the distance from APs to APs or from APs to walls, which is damn cool. All right, so I just turned on this feature, and what I just need, I need to switch back to the design, of course, and just click on the AP. And now I can see the distances between this AP and closest walls. All right, that's pretty cool. Let's try to measure the distance from this AP to others. Why not, right? Okay, I'm doing the same, just clicking once again on the AP. No, I did something wrong. Okay, distance to APs. Looks like I just selected something wrong. So here it is. Here's the distance between the APs. Pretty cool feature, by the way. And if we're talking about cool features and how we can improve our work, let's talk about the key bindings, because you don't need to click on the toolbar all the time when you would like to switch between tools. You just need to use your keyboard. It's as simple as that. For example, I would like to put the AP. I just need to hit my A button on my keyboard, and now I'm into the AP tool. Bam, here it is. That's how fast it is. I would like to add a note. No problem, just hit the N, and here is my note. And by the way, probably you already know that we moved everything to the right side panel, so no dialogues will cover your beautiful and fancy maps anymore, so you still be able to browse across it and probably leave some comments and notes, or maybe do some adjustments for the APs. And here is one cool pro tip. That's how we call it, the pro tip stuff. If you would like to open the options for your APs, you don't need to go to the right click or press this fancy icon. You just need to hover over your AP, hold Option or Alt if you're on the Windows, and just do the click. And here is the option settings on your right side. Really fast and easy and cool stuff. Okay, well, since we're concentrated on the map, let's go through some other cool stuff. And those stuff are about walls. Of course, you can play around with walls. You can spend heck of a lot of time on that. But in Ekahau, we try to make your lives easier, at least with walls, right? You don't need to draw them like one by one. You can use some other cool tools, like rectangular wall. If you just need to draw a room, that's how simple it could be. Bounce, here's the room, here's the room, here's another room. And by the way, you can also switch between different wall types. Let me just hit 2 on my keyboard, and I've just switched to another wall type. And this is the wall brick. If I press 3, it's interior office door. How cool is that? If you would like to change the key bindings, of course, you can go to the setting of the wall and change it easily. So it's as simple as that. So there are some walls that are already predefined just to make it a little bit easier to use. So yeah, this is the really, really cool stuff. And that's what you guys already saw during the last year. And as you may know, and may not, we just released 11.5 version of AI Pro. Sorry for that. And it's also packed with heck a lot of cool stuff. So let me briefly go through what we have in the 11.5. First of all is the online antenna update. Now we're able to push new antennas or APs to you as soon as possible, as soon as we'll have them in our hands. In case if you don't like the auto update, you should go to the preferences and just click here, and you won't be able to get those fancy antennas fast. But of course, with every hour release, we will include the pack of those antennas, so you'll be always ready to do proper Wi-Fi design. All right, let's move on. Next cool stuff is sorting. Now you're able to sort your AP list with the title, with the model, or with the SSID. And probably you will say, hey, Mike, what kind of SSIDs you're talking about? I never saw SSIDs here in the list. And here, what I will answer you. Now you're able to see those things, because if you press on those 3 button icons, you'll be able to add the height, mounting, model, radius, SSIDs, SOS tags. So let's try this thing. Okay, now I was able to add the height, mounting. Yeah, everything is like 0 degree. I'm fine with that. The SSIDs, of course, since this is the APs that are simulated, there is no SSIDs for them. But if you will use your project file with measured APs, you will see all of them. SOS tags. So if you have a tag, you will be able to see it from here. So let's try this kind of thing. What we'll have if we'll just turn everything off? Okay, this is a pretty fancy list. So you'll be able to see more stuff simultaneously. And if you need to see something else, you can just easily turn this on and off just whenever you need. By the way, here's another cool stuff that we added. It's the notes icons. So we a little bit improved that. Now you're able to add notes as easy as just click on this fancy icon. And if you already have those kind of notes, will tell to you that, hey, this icon means that there is a node, just like a text node. And if your AP or, I don't know, or area or the project has the icon, we will show it as this. So probably you won't able to see it right now. It depends on your internet connection, of course, but there's like a small pin here showing that there is something inside. Let me try and click on it. So yeah, here is the image attached to my node. So this is the cool stuff. And then there's another feature that was asked from some of our friends, those kind of stars, right? Time to time, you don't want to see those stars. We're fine with that. And especially for this kind of case, you're able to turn them off. So no more stars, but if you need them, of course, you can find them from the same place. Just go to the view and press My Networks star icon. So that is it, what we have for you guys in 11.5. But let me show you what we will have soon or late. So let's do this kind of sneak peek. What we'll have really, really soon. Here's another AI Pro. I won't tell the name of it, but nevertheless, let's just go really fast. What we have for you. It's like so cool stuff. I can't even have proper words of how to say that. So now we'll have the areas for you guys. You'll be able to see all your areas here. And even if you will change the color of area, of course, we will show it to you. And as so, you will be able to do the proper sorting of your areas. You can also include some info or just hide that info if you don't need it anymore. As simple as that. Then we got the nodes. Now you will have the whole list of your nodes. And we'll also show you how many nodes actually you have inside, for example, this particular access point. But that's not everything. Let's move to the inspect. By the way, we moved surveys to inspect. And here how they will look like. Now they're damn fancy. Now you're able to know who did the survey, what kind of hardware that particular guy used, what kind of, what was the speed of the guy, how long was his journey, and all other good stuff. And as always, you should be able to sort your surveys and show or hide some extra information. So that was it. That was the sneak peek stuff. And back to you, Matt and Mac.
Man, this was absolutely smashing. So guys, I'm not sure if you really use AI Pro a lot, but if you do, I'm sure that you will appreciate the practical value of these features, especially the AP list. Like for me personally, I think it's a massive thing, especially try to imagine if you're working with bigger projects where you have APs mounted on different heights, have different tilts, different types of antennas. This is absolutely amazing. The nodes stuff, how nodes are presented, the icons around the nodes, if you have a text node or a picture node or both, this is also a magnificent thing, small thing, but very, very helpful. So Mike, thank you very, very much for that. Thanks thanks to your team as well. It's like great stuff, honestly, great stuff. So that was the Ekahau AI Pro, guys. If you are new to Ekahau game, Ekahau AI Pro allows you to do a fresh design, a redesign, a look into existing live spectrum, use your laptop for surveys if that's your thing. Like we typically tend to do the surveys with an iPhone today and a Sidekick 2 connected to it, as you can see on the screen. But by all means, you can use AI Pro for that. Okay, so now let's discuss what the noise is. So we are coming back to the main topic of the webinar. So Matt, talk us through the noise and the interference. Or actually, let's start with the noise. Where do we start? What do we need to understand in order to understand noise?
Yeah, that is a great question. And noise is, if we think about it from like an audio perspective, and imagine that you was in let's say you've gone to your local coffee shop or to a local bar, and you've got lots of other people around you talking, having conversations. Perhaps there's some background music being played in the environment. Well, you can still talk to the people that you're sitting next to, but you can hear all of the other stuff that's happening around you. That's what we would kind of refer to as like this kind of like noise or noise floor, background noise is happening in your environment. And if we then talk about like what is interference, well, interference is when something specific happens with a potential device. So let's say that you're at you're in your local coffee shop and all of a sudden Mac goes in there and he orders his favorite green smoothie, and the person behind the bar goes to blend all of those nice greens together to create that smoothie. As they turn the blender on, all of a sudden it makes such a loud screeching noise that everybody kind of stops the talking, looks around and goes, oh my gosh, what was that just made that noise? It's so loud I can't hear anyone around me, and it's interrupted me, and I'm not even going to talk until that blender's finished blending. Well, that's kind of how we can think about interference in our environment. When you've got, let's say, a microwave oven or a wireless video camera that transmits occasionally in the same space that we want to use our Wi-Fi, when these devices start transmitting, then it really impacts the performance of our Wi-Fi, because our Wi-Fi will just stop talking, they will stop transmitting and not have a great experience. So that's kind of at a high level talk about what noise and interference is, but maybe we should explain a little bit how what Wi-Fi is in terms of like visualizing RF and sine waves, and then we can then take a look at some more noise stuff. You'd think after Mac had spent nearly a whole year or 2 years doing webinars, he would know how to take himself on and off of mute by now. But don't worry, Mac, I remember my first webinar too.
Of course. So what we are looking at, guys, is the sine wave on the screen. And a sine wave is a good representation of the RF signal in the air, electromagnetic energy. So we can represent electromagnetic energy in the air with a sine wave. And we need to understand how to represent that stuff. What is the sine wave? What is the amplitude, in order to understand the noise and the impact of noise on our speeds and data rates? So let's start with the amplitude. Cycle and period, we'll actually skip that here because it's not relevant for the noise discussion, but we'll talk about the amplitude. So amplitude is the height of the sine wave. And Matt, if you switch to the next slide, if you have low amplitude, the sine wave will be quite small. If you have high amplitude, so a lot of power in your signal, the amplitude grows. It's getting higher and higher and higher. So the amplitude is power, okay? The more power you have, the higher the amplitude will be. And the more power you use, most likely your clients will be hearing that signal with higher RSSI. RSSI stands for Received Signal Strength Indicator, and it's directly correlated with the amplitude. More amplitude, more power, your devices hear the signal with higher strength, okay? With higher power. And that's the quick intro into amplitude. We measure amplitude with watts, milliwatts. So these are the units, the absolute units, but actually in Wi-Fi, since we are working in very, very tiny little units, like, you know, a fraction of a milliwatt, instead of talking in like 0.000001 watt or even more zeros than that, we just talk about the changes in comparison to a milliwatt in decibel scale. So -3 is half of the original power, +3 is double, -10 is 1/10, +10 is 10 times. So it's a logarithmic scale, way easier to work with.
Awesome. So everyone's familiar with this kind of environment. So if you've got a large office environment where you've got lots of employees there, everyone's bringing in their own devices. All of their devices have got their own components. People are using Bluetooth headsets. They've got the Bluetooth mouse or keyboard or trackpad on their desk. All of these different devices in a busy environment is going to do something that's called like raise the noise floor. You remember that background noise that we were just talking about? And the more of these devices that you have in the environment, the higher the noise floor is going to be. So that means is we're going to need to have a stronger signal strength to be able to achieve higher modulation schemes, and then be able to transmit our data faster, which is what we want. And then on the right-hand side, what we really want to try and avoid having in our environment are these types of devices that cause interference. I know the most typical one that we've spoken about for years and years is a microwave oven. And a very common example is that if you're in an office environment, then it gets to lunchtime and then someone goes and heats up their burrito, and all of a sudden the 2.4 gigahertz Wi-Fi just completely stops working. Well, that's because if you've got a leaky microwave oven, that actually works on the same frequency as what 2.4 gigahertz does. So if your access points are trying to operate on those channels, channels, well, guess what? They're going to be like, oh my gosh, what is all that noise that has just been generated on the channels that I want to use? And then they're going to stop broadcasting. So we really want to try and limit the amount of these devices we have in our environments. We want to find them, locate them, reconfigure them, or remove them, or fix them if possible, to give us what we would refer to as like a clean RF environment, so you can have better performing Wi-Fi and faster Wi-Fi speeds as well. So moving on to the next slide, Mac.
Okie doke. So guys, there is a very, very important question that we get asked that question very often, okay? And the question is, does co-channel interference, CCI, create noise? Because like when you look into your fancy new Pixels or iPhones or whatever device you might have, you will have access to some applications or scripts to show you the noise, show you the RSSI, and RSSI is a signal string that your device has received the signal with. And the noise is, you know, the background noise that Matt has just talked us through. So how does a device calculate noise when it doesn't have a spectrum analyzer? Noise is a layer one thing. It's a physical thing, okay? So you can't really calculate noise reliably. And to measure noise, to understand what the real noise is, you need to peek into the electromagnetic energy itself, and you have to see the noise. And then you can use some fancy algorithms that we use to calculate the noise, but that's the real noise based on the spectrum analysis. Now, all the small devices, our mobile phones, our laptops, and even some of the access points, they will calculate noise based on the CCI, but this is not the same. This is not real, okay? So if you have a chipset, a Wi-Fi chipset in your phone, and your phone says that there is a noise of -90, and all of a sudden, 5 seconds later, there is a noise of -70, so 100 times higher, it doesn't mean that really have 100 times more noise in our environment. What it means that the device thinks based on the retransmissions rates created by high contention. So all the clients on the same channel trying to talk at the same time. If you have 5 access points, 10 APs connected to each of these APs, you now have 55 clients, plus 5 APs, plus 50 clients contending for the airtime. Wi-Fi is half duplex, only one device aims to talk, to transmit at a single time. And if you have more of these devices, then you will have more contention, and it will get slower and slower for everyone. So the co-channel interference, CCI, that we see on the screen is a problem where you have multiple radios, multiple devices on the same channel. And that does not create noise per se. That creates a contention, and devices that are not equipped with spectrum analyzers, they might use the attribute, the rate of retransmissions to calculate noise. So we will talk about that a little bit more, but it's quite important to understand that CCI, cross-channel interference, channel contention, same channel overlapping, does not create noise.
Awesome. So why don't we take a look at what does cause this noise and interference in our environments? Well, things like the Earth electromagnetic noise can do this, cheap radio components, and excessive frequency hopping spread spectrum. So effectively what we were just talking about a few moments ago, when you've got a buildup of lots and lots of devices in a congested environment, and you've got maybe lots of Bluetooth devices in 2.4 gigahertz, what you will notice is that the noise floor will get slightly higher. And when your devices are trying to talk, there's always that background noise that we can hear when we're trying to transmit and access the Wi-Fi medium. And that's kind of what if you think about it from like an audio perspective, and when we go into these places and you hear all of like this background noise when you're trying to talk, that's what we're referring to from our Wi-Fi devices. They always have this noise floor that's constantly there in the background, that's being calculated and there for them to have to kind of talk over.
Yep, and a great question from Jonas in the chat. So does APs next to each other on different channel affect power levels, example noise? So a very short answer to this question is, if you have access points on the same channels pretty much touching each other, they will increase noise due to electromagnetic field of the radios that they create on the electronic level. So if you have same APs on different channels, completely different channels, the bigger the distance between the channels, the lower the noise will be created by the RF energy emitted by these radios. But you don't want to have APs too close to each other anyway. And the higher quality, the higher, the better model of the AP, the better the design of a radio and the antenna, the more precise the transmission will be, and the electromagnetic leak outside of the access points will be lower as well. Okay, so that was some.
Well, Mac, actually, before you say anything else, I want to ask our webinar audience a question. What do you think this device here in the middle of the screen is supposed to be? Because when I saw this graphic that Mac got created by a generative AI, I was looking at it and I was thinking, what has this got to do with interference? And I can see a lot of people thought the exact same thing that I thought. I was like, since when do telescopes interfere with RF? And then Mac was like, oh no, come on, Mac, clearly this is obviously a bird watching camera. And I was like, well, hello, clearly it's not that obvious, because a lot of people in the chat agree with me that it looks like a telescope, not a bird camera.
But you have birds on the ceiling and whatever. I had like oh, there we go. My little star and description is back on the screen. Okay, guys, so let's talk about the sources of interference. What can cause interference? The bird watching camera, I actually have a real one here. So that's what the AI creative tool should have created for us. But we have microwave ovens. If you have leaky old microwave, it can kill your 2.4, especially when you're close to it. Wireless cameras of all sorts that are wireless, but not necessarily Wi-Fi. If you have a wireless camera that is not Wi-Fi, it will be killing the spectrum on a particular channel or two channels. 100% of the channels are gone. You can't use them for Wi-Fi anymore. Leaky LED lights. So when you get to the shops, to retail, to warehouses, industrial spaces, even office spaces, we've seen some LED lights that are creating electromagnetic energy that does affect Wi-Fi, and very often not only on 2.4 but on 5 gigahertz. Okay, which is bad. Motion sensors. When you have those little motion sensors in the corners of the rooms, you move next to it, and then you will see in the historic spectrum view when you're doing a survey with Ekahau, iPhones, Pixels, and the Sidekick, whatever you use, you will see like a slight little tiny narrow interference that can completely kill your transmission on this particular affected channel, very, very frequently on 5 gigahertz as well. Wireless gaming gear like headsets, game pads. When you look into spectrum to what these devices are doing, they create two quite wide channels, one main one that is used for the audio and one secondary one. If you have interference on the main one, your gaming device will switch to the secondary channel. But this can and will affect Wi-Fi, especially on 2.4 gigahertz. But that's not everything. We have even more interferers. So Matt, what do we need to be aware of when it comes to interferers?
Yeah, and actually, I want to bring Miko back. And I know you're busy replying to people in the chat. But whilst he's getting his camera on and stuff, one thing that I wanted to say is that pretty much all of these devices, they have their own unique signatures. So what I mean by that is when you take a look at all of these different devices, whether it's a wireless headset, Bluetooth, motion sensor, microwave oven, spy cameras. When you take a look at this infographic, you can kind of see in the RF spectrum, they all have their own unique signatures, which therefore means that when you walk around and do a survey with Ekahau, we can recognize these signatures because our Sidekick 2 has got a spectrum analyzer built into it that sweeps across all three frequency bands, 2.4, 5, and 6 gigahertz. We can identify these devices for you, and you'll be able to see them in your environment, which is extremely helpful because a lot of the time you can't see these devices or you don't even know that they're there. But the fact that you're able to detect them, locate them, and see exactly where they're on a map so you can find them, reconfigure them, or remove them is going to be so helpful. So Miko, I was thinking maybe you could just talk us through a little bit of an insight about what's coming early next year around our surveys, because there's a big push on helping our users keep their wireless networks and environments as secure as possible, and also being able to identify these types of devices.
Oh yeah, absolutely. So Ori, on the Wi-Fi day, we announced that on the survey app, we're going to be supporting some of the security features. So for example, identifying the rogue APs and also interference sources. And the plan was to, well, actually release it next week, but things didn't go exactly according to plans, and we had to postpone it for early next year, early January. That is. One couple of issues with the heat map refreshing and so on. So I wasn't happy with the quality. So need to wait until the beginning of next year. Sorry about that.
So you heard it here first. Miko's the quality control police. If it's not 100% perfect, then it doesn't get released. But the good news is in a very short time you're going to be able to have access to this, and then you can. Never before would it be easier to identify if you've got security vulnerabilities in your network, if you've got interferers in your network, perhaps you haven't configured your wireless networks in your environment with the strongest method of encryption that you can, you're going to be able to easily identify all of these things directly from the survey application, and then go ahead and remediate those issues as fast as possible. Yeah. No worries. Let me skip to this next slide, Mac.
Okay, cool. So now we understand what the amplitude is. We understand the difference between the noise constant and the interference, like a peaky interference in the RF space. We know what can cause both of these issues. So now let's talk about how the noise can affect Wi-Fi speeds. But before we can discuss it in a more educated manner, we need to understand this, Matt, don't we?
Yeah, so a common thing you may have heard of, an acronym in Wi-Fi, is something that's called SNR. And what that stands for is signal to noise ratio. So what we mean by that is, we've been talking about this quite a lot today, is this noise, this background noise that we have in our environments that our devices hear and need to transmit over. This is what we refer to as the noise floor. And typically the noise floor operates anywhere between -100 to, let's say, -95, -90, sometimes a little bit higher than -90 dBm. And then we have this thing here, which is called our RSSI, and RSSI stands for Received Signal Strength Indicator. So from the perspective of your client device, let's say you've got your iPhone or your Android device in your hand, and you go to a particular location and you want to know the SNR for your device. Well, there's a few things that are being calculated by your device. First of all is going to be this noise floor that is happening in the background. Then you're going to receive the wireless frame from your access point. It could be a beacon, data frame, whatever it is. When you receive that frame from the access point, you'll be receiving that wireless frame to your client device at a particular signal strength, which we refer to as the RSSI here. So perhaps in this example, you're pretty close to the access point and you receive that wireless frame at -50 dBm. So if you've got the RSSI value as -50 dBm, and we've got a noise floor all the way down here at -95 dBm, well, what SNR is, that difference between where you receive the signal to the noise floor. So in this example, if it was 50 dBm as the received signal strength, you would have an SNR value of 45 dBs. And the higher the SNR value you have is a good thing, because the better signal quality that you have will typically mean that your device can do something that's called more complex modulation schemes, which effectively means that they can send their data transmitted over the air faster, because it's easier to decode those ones and zeros over the air. So that's what signal to noise ratio means. It can vary depending on how close you are to the access point, how much interference there is or noise in your environment will affect all of this, and naturally that will impact the speed and performance of your Wi-Fi. And I really like this next slide that Mac is going to talk you through to help visualize the impact of having a strong signal to noise ratio versus a low signal to noise ratio.
Yep, I will help you visualize. Okay, guys, so when you have low SNR, so either a low RSSI, low signal strength that your device has received a frame with, or high noise or high interference in this particular time where the frame was received, you will have low SNR. Or you can have a combination of both, not too strong RSSI, fairly strong noise. Anyway, your SNR, signal to noise ratio, is low. And when your signal to noise ratio is low, it means that the usable signal that is being transmitted by a transmitter is of a low quality. And that means that you will have to be transmitting not too many ones and zeros at any given time, okay? So when a device transmits using less complex modulation with a low SNR environment, the time it takes to transmit the certain amount of data that the device wants to transfer, it just takes more time. And that device might be able to send some of its data in a single transmit opportunity. It might not finish it. It might have to come back to the wireless medium, play the game of access again to wait for its turn to finish sending the frame. And it might still not finish. It might be like constantly coming back for more. And when it has access to the medium, it will be talking very, very slowly. So not only the device will try to get access to the Wi-Fi medium very frequently, but when it has the access to the medium, it will be talking slowly, okay? And now when you compare that to a high SNR transmission, where you have high RSSI, low noise, then you can use more complex modulations. And now maybe instead of sending at a slot time 1 or 0, or maybe 2 bits if you're lucky, you will now be sending 10 bits, or in the future, 12 bits at a given time, okay? You might be talking so much faster just because of you have higher SNR. And this talking slower, talking faster, we call that the MCS rates, you know, it will affect the data rates. It's subject to a more detailed discussion. We won't have time to dive into MCS rates today, but what we want you to understand is the higher the SNR, the higher the modulation schemes, and that translates to more bits being transmitted at the same time, and the devices with higher SNR will be spending a fraction of a time when compared to devices with very, very low SNR. We actually have Gjermund in our audience here today. He has a great tool he has written to visualize the airtime utilization of your wireless frames based on the SNR, on MCS rate, on all the different attributes. You can see that, how big of a difference it makes when you have good transmission quality versus bad transmission quality.
Yeah, always great to see you here, Guillaume. And if you want to maybe post a link to your website where they can get your calculator from to see this, that would be very helpful for people. And we have a poll question for everybody. So, Mac, why don't you read it out whilst I get it all launched?
Of course. So a poll question is, how do you measure the impact of noise in your Wi-Fi network? A, I don't measure anything because I rely on lag. B, I check MCS rates / data rates on client devices. And that's an educated guess calculated by the device, right? I check noise or SNR value on client devices, and that's a calculated guess. Or D, I do a packet capture and check retransmissions rate. That's kind of a crazy guess, I would say. It's possible to have an educated, crazy guess by looking into packet capture retransmission rates. Or E, I measure noise and SNR with Ekahau Sidekick 2 to get the real measured value. We still have people voting. Actually, I think most of the audience has voted at this time.
Yeah, pretty good responses there. So what I'm going to do now is I'm going to just end the poll question, and then I'm going to share the results so we can see them.
Proper. So more than half of you guys, you are relying on Ekahau tools to measure noise, and we are super thrilled to say that this is pretty much one of very few methods that give you a very exact noise levels measured, because it's measured, right? We have spectrum analyzer and we leverage that information to give us an exact noise values. It's not calculated anymore. It was in the past, it's not today. So very, very pleased to see that. What do you think, Matt?
No, I think it's awesome that the Sidekick 2 uses the spectrum analyzer to actually calculate the amount of noise in the environment. So you get a really clear picture of the SNR of your environment for how your Wi-Fi is going to be performing. Because like we said, having that good quality Wi-Fi is going to be how your end users are going to be able to get the faster speeds from being able to do those more complex modulations. So it's really key to be able to have access to that information. And I love doing surveys with the Sidekick 2 and analyzing all of the results. Perfect. So let me close that and move on to the next slide. So yeah, great question here about how do we actually measure noise and interference? Well, we had a few answers kind of on the poll question there, but what you can actually use is your Sidekick 2. When you go to do your survey of your environment, perhaps it's an office or if it's a warehouse, any kind of environment, as you're walking around with the Sidekick 2, not only are we detecting all of the signal strengths and heat map visualizations that you would kind of expect to see from all of your access points and locate them on the map, but we are also measuring the noise in your environment and detecting any interferers that you may have. So again, we want to minimize that noise, get rid of as many interferers as possible, and give you the best possible Wi-Fi environment. So when we're talking about measuring and calculating this, Wi-Fi operates at layer 1 and layer 2 of the OSI model, the physical, medium, and the MAC layer. And what the spectrum analyzer does inside of the Sidekick, it actually measures that layer 1 physical RF energy that's in the air. And Mac, why don't you talk us through this versus the Sidekick against a device which is using its Wi-Fi radios to calculate these types of values?
Yeah, sure, perfect. So we've talked about this, so I will fly through that fast. On the left-hand side, we have a Sidekick, and we measure the noise with a spectrum analyzer on layer 1, physical layer. We measure the percentage density of the electromagnetic energy in the air with a built-in spectrum analyzer to calculate, to measure the real noise, okay? And the noise on the RF level is affected by the RF only, okay? And that means that the contention will not affect noise. Why is it important? If I have one Wi-Fi device or 1,000 Wi-Fi devices, assuming that the radios, that their chipsets don't emit electromagnetic energy other than the Wi-Fi, then they won't affect noise. We will have high contention, yes, but the physical noise will stay unchanged. When you, however, calculate the noise with a Wi-Fi chipset that does not have spectrum analyzer built in, then this is based mostly on retransmissions count, and this is based on the protocol on layer 2. So we are now seeing, okay, I tried to send 100 frames, and out of this 100 times, I had to rate shift down 83 times. I assume that the noise must be high, but it might not be noise. It might be noise, but it might also be contention. Two absolutely different things.
So when you're taking a look at the spectrum analysis data, let's say in Ekahau AI Pro, when you are looking at the live spectrum data, if you are taking a look at it and you can see these kind of, I don't know, rectangles or whatever from your, these are your Wi-Fi access points that you can see that are currently broadcasting on different channels. And what this is looking at is that layer 2 scanning. So we are demodulating anything 802.11 related from the beacon frames here. And this is where we can see the things like the signal strength from your access points. We can see what channel they're using, the channel width, and we get all of that good information that we can see here. But that's what you're looking at when you're just looking at this graph with these visualizations enabled right now. However, if you want to see the layer 1 information, the spectrum analysis information of the RF energy that's in the air, which can pick up anything that's Wi-Fi or non-Wi-Fi, then you will need to have your Sidekick or Sidekick 2 connected with its inbuilt integrated spectrum analyzer. And that's where we're going to see this beautiful spectrum analysis, and we can see how much energy is being transmitted over the channel at any given time. So one of the things that I like to do is when I've got my Sidekick 2 connected to my Ekahau AI Pro, and I want to see, visualize what's happening over the air, I like to connect my phone to my access point and run a speed test, because that forces a big push on the upload and then the download. So it means the traffic on the channel gets very busy, and you can see that information and energy transmitted across the channel. Also, what we would see here as well, if we had any interferers in my environment, let's say I had a video camera or a passive infrared device that was operating 5 gigahertz, this is where we would see that signature and that detail in this view right here.
Okay.
So Mac, how do we optimize our environments if we've got noise and interference?
That's a very good question. So let's switch to the next slide then, and I'll quickly talk about that. So we know what the noise is, interferences, differences between the spectrum analyzers and calculated noise. we know that now. Okay, so now let's talk quickly about how can you improve your dire situation. So if your devices are slow, if your data rates, MCS rates are slow, what can you do about it? So on the left-hand side, we have increased RSSI. So increasing RSSI will improve your SNR, okay? If you increase your RSSI, received signal strength indicator, without increasing noise at the same time, then your SNR is higher, then you're going faster. To increase RSSI, you need to have correct physical design, because if you don't have enough access points, you don't have enough radios, you have wrong types of antennas, you cannot have a good RSSI, right, consistently. So you need to start there. The same goes for transmitting power level. And our aim pretty much always is to match the transmitting capabilities of our devices that we are serving in our Wi-Fi network, okay? So it makes no sense to go very low on transmitting power level on the AP level, on the radio level, and it doesn't make sense to go very high, okay? So we need to shoot somewhere in between, like 14 to 17 dBm typically with internal omnidirectional antenna is a sweet spot. So that's how you increase RSSI. Matt, how about decreasing noise? What would you do?
A simple answer, realistically, is that the 2.4 gigahertz band, unfortunately now, is just, in most scenarios, I'm going to say 9 times out of 10, is not capable of providing business critical Wi-Fi in that frequency band anymore, because there are so many devices that operate there, Wi-Fi and non-Wi-Fi related. Also, the lack of non-overlapping channels that we can use in the 2.4 gigahertz frequency band. So I would really recommend that we move to 5 and 6 gigahertz for all of our business critical Wi-Fi networks, if possible. And if you have any interferers in your environment, let's say like these devices we've spoken about earlier, identify them, locate them, reconfigure them, or if possible, remove them from your environment that are going to be causing you interference and therefore lots more noise. But also, if you have these devices in your environment, then your access points and client devices, they're just not even going to operate on those channels typically where they'll be working. Another thing that we can do, which I'm actually going to show you, which is quite a cool thing that I thought when I first saw it, especially when I was looking in Ekahau, is the fact that if you have got a very noisy environment, one of the things that you can do is if you actually use a more narrow channel width, that will also give you possibly the best possible signal to noise ratio value for your access points and your client devices, because something happens when you double the channel width with your access points radios. And rather than talk about it, I would actually like to just show you some demos inside of Ekahau. So first of all, first demo is I'm going to show you what we've got here. And we've got a design for a fairly large office. It's got a typical kind of office space, canteen, meeting rooms, and we've got a bit of an auditorium here. And everything's all green. So this looks like a good design. So I guess I must have done this design. But if I was to, perhaps change some of the visualizations, and maybe I'd want to look at the capacity of the network currently, because what I actually have here is my area is configured with a bunch of devices. So I've configured some capacity requirements for this project, and we've got 500 devices here that are capable of doing Wi-Fi 6 and Wi-Fi 6E, laptops and smartphones spread evenly across this network. So when I take a look at, let's say, the signal strength, everything looks good. I know there's a lot of people here new to the webinars and perhaps new to Ekahau. So what we can see here is a simulated design that I've done inside of Ekahau AI Pro. And I'm just going to change the visualization on the 5 gigahertz frequency band to be, I don't know, how about the secondary signal strength? It's all green everywhere still, so that means it's looking good. But how about if I was to change now, and I wanted to ask Ekahau, hey, can you calculate the health of the capacity for all of these client devices in the environment? Well, I can actually change the visualization here to capacity health, and all of a sudden, it all goes red. So I guess actually it must have been Mac that designed this Wi-Fi network, because I wouldn't have any red in my designs in Ekahau AI Pro. Well, why is it red? And that's a good question. And if I zoom in a little bit, And what you might notice is I saw people ask earlier in the chat, like, what are these numbers next to the access point icons? And it's a great question. So if we take a look at this one here, you can see it's got a 1, a 36, a 1, and then an @ sign, and then a 40 symbol. Well, this is actually telling you the frequency band and the standard of Wi-Fi that is being used and the channel that is being used as well. So in this example, it's using channel 1 on 2.4 gigahertz, channel 36 on 5 gigahertz, and then channel 1 on 6 gigahertz, but it's using a 40 megahertz wide channel. And if you take a look at all of the other APs around, you can notice that they're all on the same channel. So the performance of the network isn't very good because we've got all of the access points by default in the environment sharing the same channel. So that's interesting. And you can visualize that in another way by changing this visualization here to the channel interference view. And you can see everything kind of goes gray down here. And if I was to hover my mouse over any position on the map, you can see in this location, we have got 13 other access points all operating on the same channel. So when you've got more devices sharing the same channel, it's gonna be more contention, less chances for your devices to access the medium and have a good time on the Wi-Fi. But we can dive a little bit deeper. So if I go to the inspect tab and I've clicked on, and I'm going to stay in this same location. So pretty much where this A is in the auditorium. And if you take a look at what we can see on this top right-hand corner, again, we see our signal strengths for primary and secondary. And then here we can see that the signal to noise ratio is 50 dBs currently. And the data rate, the theoretical data rate that can be achieved right now is 573 megabits per second. But if I change this visualization here from channel interference to the data rate visualization, okay, now in this location, you can see here the details for my simulated client devices that I've got down here. You can see that we can achieve a data rate of between 285 to 300 megabits per second. And the actual data rate is here, the 287 megabits per second. So why do I see a data rate here of 287 megabits per second, but I see 573 megabits per second up here? Does anybody know that before I reveal the answer? People let us know in the chat if you know why there's a difference in data rates here and here. Dun, 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 dun. Well, the reason why there's a difference in data rate is because on the top right-hand corner, this is showing you from the perspective of the access point, and the access point has more spatial streams, 4, compared to the client devices down here that have 2 spatial streams. So the theoretical data rate for these devices in this location currently is at 287 megabits per second. So that's why you will see a difference here. And I have a question for you now. I'm going to fix the channels in the design, so we have completely no overlapping channels for the project. Do you think that the data rate is going to change, improve, get worse, or stay the same for our client devices? Let me know in the chat whilst I show you how we can fix the channel plan. Stay the same, improve. Okay, interesting. So what I'm going to do now is I'm going to head back to the design. Everyone's saying improve, improve, improve. Okay, so what I'm going to do is I'm going to click on this button here, which is the channel planner wizard. And once I've got it selected here, I can basically ask Ekahau to reconfigure all of the channels of the access points in my environment at really just a click of a button. So what I'm going to do is I'm just going to enable all of the 5 gigahertz channels, and I'm going to keep it. Currently the channel width is at 20 megahertz wide. Oh, I love what Alan said. It's going to explode. Okay, well, if AI Pro explodes, we've got the right people on the call, because Mike and Miko will be able to fix it straight away, I'm sure. But hopefully we don't see any exploding access points. Okay, so I've got all of the 5 gigahertz channels selected, and they are 20 megahertz wide. If I hit create me a plan now, what Ekahau does, it runs through all of the access points, and you can see straight away my 5 gigahertz channel interference has now gone to 100% passing. So we've got no channel interference. If I go back to the channel interference view, you can see everything's all green, all good. Life is very well. So let's now go back to the data rate and go back to the inspect tab. I'm in the same location, and now look, data rate has stayed the same. So the answer is that even fixing the channel interference, the data rate didn't change for my client devices. Interesting. Okay, another thing that I found very interesting to see and visualize, especially in Ekahau AI Pro, is that the let's look at the SNR values right now. Okay, so the signal to noise ratio from the access points perspective is 49 dBs, and the SNR is at 46 dBs for the client devices. And if I change to the noise visualization view, we can see that the noise floor here is currently being calculated at around minus 95 dBm. But I want to try and do something different again. And I'm going to go back to the data rate view. And this time now, I'm going to ask Ekahau to recalculate the channels. But instead of using a 20 megahertz wide channel on 5 gigahertz, I'm actually going to ask it to use a 40 megahertz wide channel. So I'm going to double the width of the channels in Ekahau AI Pro for the access points. And hit create. And what it's going to do is going to run through all of the access points for me. And you now see this at symbol and 40 megahertz here. What do you think is going to happen to the SNR value of the client devices and the access points? Do you think they've gone up, stayed the same, or gone down? Okay. Okay, just watching the chat.
We've got 50-50.
Nice. Yeah. Okay, so I'm going to go back to the inspect tab. And what you'll notice here is actually it went from 49 dBs to 46 dBs for the access point. And for the client device, it went from 46 dBs down to 43 dBs. So that meant that the signal to noise ratio value effectively got worse by 3 dBs. Well, why is that? That's because each time you double the width of the channel for your access points, you actually bring in double the amount of noise. And when you double something in Wi-Fi, effectively you have an increase of 3 dBs. So that's why we're seeing this SNR value go down. And if we was to take a look at the noise value here, you will notice that it's gone down. The noise floor has now gone up by 3 dBs. So that's why I wanted to show you in Ekahau AI Pro, because I think this is really nice to visualize and see here, is that sometimes if you want to improve speeds, performance, and the overall behavior of your Wi-Fi network, sometimes you're going to want to use the most more narrow channel width, because if you leave it on the defaults of really wide channels, or you're trying to use even like a 40 megahertz wide channel, sometimes in some situations, your client devices will be paying the price of a poorer SNR value, which will therefore mean that they have less chance of doing a more complex modulation and then sending their data slower over the air, which therefore means that the overall speed of the Wi-Fi network is going to be slowed down. So big tip here, we always say, when it comes to your Wi-Fi designs, deployments, optimizations, use the widest channel that you can until you can't. And what we mean by that, if you can have a really clean RF environment and use wide channels and good signal to noise ratio for your client devices by using 80 megahertz wide channels, that's totally fine. But if you don't have great performing Wi-Fi and people are complaining and you've got lots of channel overlap and interference and you're using wide channels, then perhaps it'd be better to go down to a more narrow channel, have better SNR and overall better quality Wi-Fi for your environment. So that was a quick demo of using Ekahau AI Pro. I hope you enjoyed that. I can see that we're running a little bit over, but Mac, I think you have a quick demo you wanted to show everybody as well.
Yeah, mine is super quick. But Matt, that was amazing. Thank you very much, mate. It was good, brother. Okay, so guys, I have like a little bit more fun stuff here. You know what that is?
A Wi-Fi sound tester, and do not say it's anything else. We are being recorded.
So that's the signal generation for educational purposes, okay? It's
Yes.
not a noise generator at all, okay? I will put it farther away from me, okay? I will put it on a windowsill. And on the other hand, I have my trackpad, my mouse, but I connected a cable to it just in case, okay? My educational signal drops off my peripherals, so I can't show you anything. So now Matthew has talked us through the high CCI situations, and we've seen that the high CCI doesn't affect the data rate, but it does affect the speeds, okay? Capacity, it does a lot. So now I will show you the high RF noise environments where both data rates and speeds are affected. So let's take a quick look into that stuff. Okay, so I will quickly share my screen. desktop 1. There we go. And I will share my iPad. This is really going to be quick, assuming that it works. Screen mirroring, waiting for my MacBook Pro to appear. There we go. So you should see my screen there. Okay. It might be a little bit slow for you because like the frame rate will not be perfect through Zoom, but it should be fine. Okay, I am connected to, oh, I disconnected from the Wi-Fi network. So let me connect to the Ekahau Webinar 2. That's the 2 gigahertz only Wi-Fi network, okay? So I will be connected to that, okay? I am connected to Ekahau Webinar. I will go back to Ekahau Analyzer so you can see that. I have connected Ekahau Sidekick. I have connected my beautiful Ekahau Sidekick to my iPad, and I'm showing you the screen from my iPad. You can see on 2.4 gigahertz on my screen that I have quite a lot of transmissions on channel 1, 6, and 11 on Wi-Fi, but all the other stuff, like all the peaks there, like peak here, peak there, peak before channel 1, these are all BLE in my environment. I have quite a few, and all the like a green halo or whatever it's called in native English, it's the noise, okay, or like a persistent interference kind of thing. Okay, so now before we continue, let's go to speed test, a very scientific test, okay? I'm going to UCLA speed test. I will hit go and see what happens, okay? So my 2.4 is very heavily utilized, but still, I can see like, you know, being around 10, 13 milliseconds, and I'm getting 70 megs of download speed, and probably I will have like 50 or something like upload. Yeah, there we go. So I can see just the
such a slow backhaul, man. You should have time to get an upgrade.
Well, I have, I don't know, 80 Wi-Fi devices on 2.4, so 2.4 is slow. It's gonna be slow. But now let me go back to the analyzer. Shall we? Let's go back to analyzer. And now look what is gonna happen. I am on 2.4 now. The app is loading. Okay, it's loaded. Now I take my educational signal generator. I turn it on. Okay, I turned it on. Look what happens. Look what happens here on the bottom part. Okay, it's like I am hammering my 2.4 gigahertz environment with noise at a decent level of like 85, 75 dBm. Okay, so I have a fair amount of noise now. And now when I have my iPad on that side and a generator on that side, they are 1.5 meters apart. My SNR is still quite solid. Okay, so you still see my screen. This device is like 1.5 meters away from the signal generator, or the RF generator. I will test again and hope you can still see my screen. Ping is still high. Okay, and now I'm moving my iPad closer and closer to the noise generator. Can you see what's happening with my speed? Even closer. If I bring it too close, I will drop off from Wi-Fi network. Okay, so now I'm like 1 meter away, but look how I'm affecting the Wi-Fi speed. So even closer, and now farther away, and it should pick up momentarily. Come on, iPad, be a good iPad. It's farther away, and it will start speeding up again. Okay, so I've just proven that the noise does affect speeds. And with that beautiful last quick test, we just wanted to conclude the webinar and hope you like what you've heard, what you've seen today, and understand a little bit more why you want to have noise-free environments to enjoy good speeds of Wi-Fi. Mark, introduce your kit. You don't have to ask me twice, man.
So this is concluding the webinar for today, but we will stay on for a few minutes more whilst Matt gets his rather large cat and answer as many questions in the Q&A and in the chat as possible. But this is the last webinar of 2023. And if you would like to join us and be ready for the first webinar of 2024, you can go ahead and scan that QR code and get yourselves registered. We've got a really awesome guest joining us who's an ECSE instructor legend, and it's going to be all around the fundamentals of what you need to know for Wi-Fi for 2024. Building that good foundation of knowledge to make sure that you have the best possible Wi-Fi environment for next year.